Your EV can lose power before you even press the pedal, and the thief is tiny, invisible, and hiding inside the battery pack. Today we'll dig into internal resistance, what it is, why it's killing charging speed and wastes energy, and how engineers at BYD fight it with clever cell design, bigger current paths, and better materials. Stick around, by the end you will get why a tiny ohm can cost you minutes at the charger, miles on the range, and a small fortune in wasted heat. Imagine water flowing through a pipe. If the pipe is narrow, water fights to get through, pressure drops, and you lose flow. Internal resistance in the battery is the same idea, but for electrons. The battery wants to move current out to the motor or accept current from the charger. Internal resistance pushes back. The higher it is, the harder the battery has to work to move the same power, and the more energy becomes heat instead of motion. Internal resistance has a few parts. There's the resistance inside each cell, the electrodes, the electrolyte, and interface between them. There's a contact resistance where tabs and welds meet bus bars. There's resistance in the connectors, wiring, and the pack's architecture. All of these add up. When you ask for a big burst of power, hard acceleration, or fast charging, that sum becomes a massive limiter. Why does this matter for charging speed here? Chargers push electrons into battery. The charger can deliver huge current, but the battery will only accept what the chemistry and resistance let it. High internal resistance means more of the charger current it turns into heat inside the cell instead of charging the battery. So the battery management system throttles the current to avoid overheating. The practical result: slower charge, longer waits, and more thermal stress. Heat is the enemy here. Heat speeds up bad chemistry, weakens the lifespan, and can change safety margins. Heat in the right place at the electrode increases the chance of side reactions and long-term capacity loss. That's why reducing internal resistance is not just about speed, it's about keeping the battery healthy for years. Now let's zoom into how engineers actually attack internal resistance, with BYD as an example here. BYD didn't get lucky. They reshaped the current path and the cell chemistry to move electrons with less friction. First, optimize cell design. BYD tweaks electrode thickness, porosity, and coating uniformity so ions can move more freely. Thinner coatings mean shorter ion travel distances, but there's a trade-off with energy density. BYD finds a balance, a structure that gives low resistance while keeping good storage. They also use electrode formulations that conduct ions and electrons better under high loads. Second, larger current paths. This is mechanical but crucial. Thicker tabs, bigger welds, and beefier bus bars give electrons a less resistive route out of the cell. Think of the upgrading a garden hose to a fire hose. Bigger copper pads, lower contact resistance, and welds, and better bus bar layouts all reduce ohmic resistance. BYD's engineering teams pay attention to every millimeter of metal where the current flows. Third, high-quality materials. Pure copper conductors, better plating, and improved electrolytes make measurable differences. A small improvement in conductor purity or contact plating can shave microohms off the total resistance, and those microohms add up across hundreds or thousands of cells. Fourth, precision manufacturing. Even the best design fails if the welds are messy or the tab alignment is off. BYD invests in automated, high-precision production to keep contact resistance low and consistent. Consistency matters because one bad joint in a long string of cells creates a hot spot and ruins the whole chain's performance. Fifth, thermal design and cooling. Low resistance helps, but heat still occurs. BYD uses targeted cooling where heat matters most and distributes current paths to avoid local hotspots. A cooler battery has lower resistance. Temperature and resistance are linked, so good thermal control and low resistance amplify each other. Sixth, battery management systems. Smart software measures internal resistance dynamically and adjusts charging profiles. If the BMS detects rising resistance or local imbalance, it can route charging to reduce stress, perform balancing, or trigger preheating. Software plus hardware equals better real-world performance. Here's the tough part. Every solution has the trade-offs. Thinner electrodes cut resistance but reduce energy per cell. Bigger bus bars and thicker copper add weight and cost. ultra-pure material costs more. Tight manufacturing tolerances slow production and raise prices. BYD balances these trade-offs to make a product that's fast, reliable, and affordable, enough for the mass market cars. Another challenge is long-term change. Resistance can grow over time. Repeated fast charges, high temperatures, and mechanical stress can increase contact resistance or damage the electrode structures. That's why early gains in charging speed must be proven to not accelerate degradation. Engineering must show that low-resistance designs keep their advantage after thousands of cycles, mileages, and seasons. Finally, system-level constraints matter. Lower internal resistance lets you push more power, but the rest of the vehicle must handle it. Cables, contactors, inverters, and thermal system must all scale. You can't just make one piece super capable and ignore the rest. So how do engineers push further? There are several clever levers that BYD and other leaders use, often together. Material science. BYD optimizes electrode binders, an additive that reduces impedance. These tweaks change how ions and electrons move at microscopic scales. Additives can form better solid electrolyte interfaces that remain stable under high currents, preventing resistance creep. Cell geometry. By changing tap placements, electrode lengths, and jelly roll layouts, BYD reduces the distance current must travel inside the cell. Flat pouch designs or large prismatic cells can be optimized differently than cylindrical cells. Choosing the right cell form factor matters for internal resistance as well. Packaging. BYD's pack design often includes wider conduction plates and direct low-resistance routes between cells and the main busbar. They think about electric flow as the map. The shorter and wider the highways, the less traffic jam you get. Cooling integration. BYD ties cooling channels close to high current paths. By removing heat where the current concentrates, they keep resistance low and consistent. Thermal management and electrical designs are co-developed rather than treated separately. Here's the manufacturing finesse. Precision welding, laser trimming, and inline resistance checks stop defects before they become problems. BYD's factories use robotic cell welding and automated quality checks to ensure every joint meets low resistance specs. Software intelligence. BYD's BMS monitors resistance across strings and can balance current, perform adaptive charging, and trigger maintenance actions. Even detecting small resistive increase early lets the system manage stress and extend life. Testing and validation. Real-world stress tests, rapid charge loops, thermal cycling, and long-term aging prove the design holds up. BYD runs these tests to simulate years of use in weeks. The data then loops back to tweak materials and process. Here's a simple checklist engineers use when minimizing resistance. Reduce current paths, length, and increase cross-section area. Use thicker taps and bus bars. Optimize cell layout for shortest electron route. Improve contact quality and welding consistency. Automated welds and inline resistance checks. Use better conductive materials and plating. Copper purity. Better coatings to stop corrosion, optimizing electrodes and electrolyte for lower internal impedance, tailored binders and additives. The turning point comes when these pieces all work together. Lower internal resistance doesn't just shave seconds of charge time. It changes what's possible. With lower resistance, a car can accept higher current without overheating, meaning faster top-ups and less energy wasted as heat. The inverter runs cooler. The cables can be lighter, and the cooling system shrink. Those changes add up: more range, faster charging, and lower operating costs, and better real-world range. Here's a quick example. Imagine two identical cars with identical battery except one has optimized resistance. At the same charger, the low resistance pack accepts higher currents longer before throttling. So it gains more state of charge faster. It heats less, so the BMS allows higher sustained power. Or a single charging session that may mean minutes saved. Over hundreds of sessions, that means the battery ages less and delivers more miles over its life. That's the real win. Lower internal resistance gives you immediate user benefits and long-term durability benefits. if the design and manufacturing back it up. Internal resistance is a small number on paper, but a giant enemy in practice. It steals power, slows charging, creates heat, and shortens battery life. BYD's approach, optimizing cell chemistry, widening current paths, using high-quality materials, precise manufacturing, integrated cooling, and smart BMS, shows how a company can aggressively attack resistance from every angle. This isn't magic. It's a careful engineering, iteration, and scale. BYD's move illustrates that to beat the hidden thief, you must think from the electron's point of view. Make the route smooth, wide, and cool. Do that and EVs charge faster, run longer, and cost less to live with.